Okay, on to related rates. So like I said, in this unit, we're jumping all around. Now we're back to chapter 2. So this was the one section we didn't cover in unit 2A, related rates. As a heads up, this is going to be mostly story problems. I'm sure you guys are super excited about that. What we're going to do though is come up with a plan of attack so that they all have similarities. And I think that'll help us to think through them. Okay, so let's stay positive. Earlier this year, we talked about calculus as the mathematics of change. So we were looking at derivatives, increasing, decreasing. We're looking at rates, hence the related rates. A lot of this is going to be with respect to time. Okay, so first of all, what we're going to have to do is we're going to have to extract sentences from these story problems and interpret them in a calculus meaning. So we're going to try that on A through D, just looking at these little sentences. So John is growing. Doesn't that mean something is increasing? It's his height. So we'll say dh over dt, the change in height with respect to time, is going to be 3. Because it's growing, it's positive. Also, we're in inches per year. I want you to notice how these match. Look at height is in inches, time is in years. Okay, that'll help you to match those up. My mutual fund, oh no, it's shrinking. So we'll say the change in the mutual fund with respect to time. Because it's shrinking at 4 cents, we have a negative. That's measured in dollars per day. Okay, again, the mutual fund is measured in money. Time is in terms of days. Okay, now onto some geometry stuff. The radius is increasing. Because it's increasing, we know it's positive. And we'll say the change in the radius with respect to time. Looking at this again, radius is in feet, time is in hours. Okay, last one. The volume is decreasing by 2 cubic inches. So a lot of times, guys, they're going to tell you, like they'll give you the units, but they might not say volume. So when you see cubic, I want you to think inches. I want you to think volume. So if we have 2 cubic inches per second, that's the change in volume with respect to time. Again, volume in cubic inches, time is in seconds. Okay, here are the steps that I want you to follow when we go through these related rates. I'm not going to read through them right now. That is so very boring. As we go through the problems, I'm going to refer to these, okay? So really these, there's going to be 5 steps that we'll go over. This is broken out a little more detailed. So again, I'm going to reference this while we're working. They're just typed for your reference later. Before we get to some story problems, though, let's knock out just some basic problems looking at derivatives. So we have x squared plus y squared is 25. And x is 3 and y is 4. So we're looking at this moment in time, right? Like we could look at this and we could say, well, what happens if x is 0, y could be 5. In this case, we're looking when x is 3 and y is 4. What this means is the change in x with respect to time is 8. We need to find the change in y with respect to time. Okay, so here's what we're going to do. If we want a dx dt and a y dt, we're going to apply the operator d dt to both sides. Okay, so we have this function here. What's the derivative of 2 of x squared? That's 2x. But remember, you're applying the operator with respect to time. So it becomes 2x dx dt. If we applied the operator d dx, remember, to x squared, it would just be 2x dx dx. But now because it's dt, if I apply the operator d dt to x squared, it's going to be 2x, and then the derivative of the inside stuff with respect to time is dx dt. Okay, going on, plus 2y dy dt. What's the derivative of a constant? 0. To clean this up, do you guys see we can divide everything by 2? So I'm going to get x dx dt plus y dy dt is 0. Now, if you didn't divide by 2, totally fine. After we do this, so this is going to be the procedure. We are going to figure out our equation, which they gave it to us. Okay, we're going to take the derivative, and now we're going to sub in the numbers. Now look, they asked us to find dy dt, which is this. In order to find that, doesn't that mean I have to know everything else? So I'm going to replace this x here. Oh, we lost the problem. Okay, I'm going to replace this x here with a 3. I'm going to replace dx dt with an 8, and I'm going to replace y with a 4. So let's go ahead and do that. X is a 3, dx dt is an 8, y is a 4, I don't know dy dt. Now, we're lucky that that's the only unknown, so that is totally okay. We are now going to subtract 24 to the other side. And then now we can get our final answer. Dy dt is going to be -6. Notice that I don't have any units because this had no context. Okay, so I just wanted you to get the procedure down. Okay, now we are going to follow the pattern of those numbers listed, the outline on the first page. I'm going to use this acronym. I don't know what it could stand for. I haven't come up with something fun. Street FDS. I don't even know. Okay. I think there's a company called Floral Delivery Service or something. But if you guys come up with something good, that would be great. I've been trying for years and have not come up with something. Okay. So the S stands for sketch. So we have space over here. So we are going to sketch. We are going to make a table. There's our ST. Then we are going to come up with our formula. We are going to find the derivative, and we are going to solve. So this is going to be a 5-step process. We are going to take this story problem and make it not complicated by doing this. So the radius of a circle is increasing at this rate. Let's draw our circle. First step is sketch. In our picture, we are going to put units. A circle has a radius. Then our table. Our table is going to have constants. It's going to have changing, and it's going to have rates. A constant would be anything that doesn't change over time. It's not uncommon, or let me make this a little more clear. It's very common that this will be empty. Okay, so don't be surprised if that's empty a lot, but we want to keep our eye out for it. Okay, so look at the next one. It says the radius is increasing at a rate, guys. Doesn't rate mean derivative? And look at feet per minute. Okay, so we have this rate. So we know it's going to go over here, and it's 5 feet per minute. Now, here's where the example, the activity that we did on the first page, it says the radius is increasing. So the radius is changing with respect to time. Find, underneath the table, I'm going to write what we're finding, the rate of change of the area. That means how fast the area is changing, which is the derivative with respect to time of the area, when the radius is 10 feet. Now, it just says 10 feet. That's clearly not a rate. But is it constant or is it changing? Well, if the radius is increasing, what happens is this radius keeps increasing and increasing and increasing. We are stopping when it's 10. So when it's 10, whatever that is, that's what we're going to use. So that's a changing value because it's always changing. Step 3, come up with a formula. Well, we're talking about area. Let's use the area of a circle formula. It's never going to be a formula, guys, that you're not familiar with, okay? So don't worry about that. 4, take the derivative with respect to time. Time drives all of this. And if you notice here, you have dt's in the bottom. It's with respect to time. So it's going to be dA dt. Pi is a scalar. What's the derivative of r squared? It's 2r, and the derivative of r, remember, it's like chain rule. So you bring the 2 down, r to the first, and then apply the operator dt, and you get dr dt. At this point, did you guys notice the constants was empty? If there was a number here, we would have to sub it into this step before we take the derivative. Finally, let's solve step 5. So we are going to replace everything we need. It says to find dA dt, so that's okay that we leave that the way it is. Then it says 2 pi r. R is 10 feet and dr dt is 5. So let's go ahead and fill this in. So 2 pi, r is 10 from the table, and dr dt is 5. So this is going to give us 100 pi. Now we need units. Look at what we have here. We have area up top. If I'm dealing with feet, would an area be feet squared? Over time, because it says dt, which is minutes. Please make sure you guys throw your units on there. Okay, if you need to double check too, look at this. This 10 is in feet, and the 5 is in 5 feet per minute. So feet times feet gives me my feet squared. Okay, this is the 5-step process. Apply this to everything, and we'll be a-okay. Okay, 4, a right triangle. Right away, it's saying, hey, make this your picture. So a right triangle has sides 30, and 40. When we make our right triangle, you can use X, Y, and R, or A, B, and C. Let's see, on this one, what do I want to use? I'm going to use X, Y, and R. It doesn't really matter, I'm just labeling it. Okay, and then that's our first step. Constant changing rates. Remember, it's not uncommon to have the constants empty. Okay, let's start reading them. It said it has sides 30 and 40 inches who are changing. Do you guys get that even though they're 30 and 40 now, that they're going to be changing? So the sides are 30 and 40. We're putting them in the changing column. They're not fixed. The length and width are increasing. Okay, here we go. Let's call this our length and this our width. It doesn't really matter though because they have the same rate of change. Notice that it says rate right in the problem. Okay, it doesn't have to say rate. They could just infer it from what they write. But also inches per second. Okay, so we're going to say dx dt. That's our rate. X is changing with respect to time, and it's going to be 2 inches per second, and then dy dt is also 2 inches per second. How fast is the area changing? Okay, step 3 is our formula. A equals, not pi, this is not a circle. What's the area of a triangle? Half base times height, so in this case, it'll be half x times y. Remember here, if there's any constants, we're going to sub them in. There are not any, so we go on to the derivative. Okay, the derivative. The derivative of a with respect to time is dA dt. Oh, you know what I didn't write? Our find. We want to find dA dt. That's how I knew to use the area formula. Okay, half is a scalar. Now look here, we have product rule. We have a first and a second. Remember, product rule says first, what's the derivative of y with respect to time? dy dt. Plus the second, which is y, what's the derivative of x with respect to time? dx dt. Now we should have everything in our chart that we need. Look at, we have an x, we have a dy dt, we have a y, and we have a dx dt. So now, step 5, I feel like this is the easy part now, subbing our numbers in. So dA dt is going to be a half, and then 30 times 2 plus 40 times 2. So using the numbers up above, and if you do the math, that's going to be 60 plus 80, 140. Half of 140 is 70. What units? Use this as your guide. What's area in? Inches squared. What's time? In seconds. So we're going to have inches squared per second. Okay, on to the next one. How fast is the hypotenuse changing? So we have the same picture and we have the same chart. So how about we just make a new formula? If they're talking about the hypotenuse, now we're going to find how fast dr is changing. Okay, so now I have a different formula. The formula is going to be x squared plus y squared equals r squared. Okay, on to step 4, finding the derivative. It's going to be 2x, and then the derivative of x is dx dt. Remember, we're taking the derivative with respect to time. Plus 2y dy dt equals 2r dr dt. Okay, I hope you guys are seeing that all these 2's cancel. That's always nice. And now we're going to start subbing some numbers in. So now we're on to 5. Look at our chart up above. X is 30, dx dt is 2. Y is 40, dy dt is 2. Oh, okay, now we're stumped here. We need an r. Look at it, it says right here that we have an r, but there's no r in our chart. Okay, let's come back to that and let's just keep going. So then we have equals. I'm going to put a little blank here. We need r, and dr dt is allowed to stay a variable because if you remember, that's what we're trying to find. See if you can figure out how to get r. Okay, well, even though this is changing, what happens when this is 30 and this is 40? Do you guys remember your special triangles, 3, 4, 5? So 30, 40, 50. You also could have done Pythagorean theorem to get it. The hypotenuse is not always 50. It's just at this moment it is. And that's how I get my number there. Okay, if we clean up the left side, we're going to have 60 plus 80, which is 140, equals 50 dr dt, divide both sides, so dr dt is 14 over 5. Now, what units need to go on this? What is radius measured in? Inches. And what, so I got that from here, radius. And what's time measured in? Seconds. Okay, so you're going to see a couple examples today. This is just going to give you a snapshot of some problems you could see. There, like I said, there's so many that we could have. Okay, read over this next one. It's saying a boat is pulled into a dock by a winch that is 12 feet above the deck of the boat. The winch pulls in rope at a rate, determine the speed. Okay, right away I can see how your head can be spinning a little bit. There's a lot going on here. What happens is you have this boat in the water. Okay, this is going to be the dock up here. This is, let's read over this again. It pulls in the rope. So can you imagine if this is the winch up here, this is the rope. So the rope is attached to the boat and you're pulling it in. Okay, so this is going this way. Okay, as you pull the rope in at that rate, you want to find the speed of the boat. So do you get this? The boat is being pulled into shore also. Let's give this some variables. Let's use X, Y, and R again. And let's go to here. Constant, changing, and rates. I love this table. I think it's so helpful. Now we're going to go number by number and just start classifying. This 12 feet above, do you guys see that that 12 feet above is always the same? Like if you're standing here on the dock and you're pulling this rope in, let's say you are the one doing it, right? You're not moving. The rope is coming in, the boat is coming in, but your position here at 12 feet is not changing. Now we have our first constant. Y is 12 feet. Go to the next number. The rope goes in at 4 feet per second. They also said rate, so we know it's here at 4 feet per second. And where's the rope? It's R, dr dt is changing. Now, did you notice something that I should have fixed? As this goes in, so as this rope goes in, do you get that this length is decreasing? So we're going to have a negative amount here. Determine the speed of the boat. So find the boat is traveling on the water, so that's dx dt, when, so here's a changing value because it's not always at this moment, but when the boat is, when there's 13 feet of rope out, I'm sorry. So we want to find the speed of the boat when there's 13 feet of rope. Where is the rope? The rope is R. Okay, so we are going to use Pythagorean theorem here. Now this is the first time we had this case where we're actually going to sub in a constant. The constant in this case is 12. And that was our Y. Okay, so now look what we get. And here's why this is so important that you do this in this step. In step 3, after you come up with the formula, sub in your constants. Okay, now that we have that, now when we go to step 4, which is take the derivative of x squared is 2x dx dt. Now look here, the derivative of a constant is 0. If you guys forgot to sub that in, this would become 2y dy dt. And look at, we have no dy dt anywhere up here. Okay, so that's a clue that that's, if you made that mistake, how you would know you made it. The derivative of constant is 0. The derivative of r squared is 2r dr dt. Again, this 2 is here. Let's get rid of that. So now I have what's left. At this point, we should be able to sub our numbers in. We have x. I don't know what x is. Okay, let's keep going. I do know that dx dt is what I'm trying to find. I know that r is 13 and dr dt is -4. Now remember we did like something like this on the last problem. If I know that y is 12 and r is 13, I should be able to find my x, and that's what's missing up here. Do you guys remember the special triangle 5, 12, 13? If you don't remember it, Pythagorean theorem will work. Okay, so now dx dt is going to be -52 over 5. What units? What is x measured in? Do you guys see this dx dt? X was measured in feet. And then the bottom, which is time, that's measured in seconds. Okay, so on B, I'm going to set it up, but I'm going to let you guys finish it. It's very similar So I'm going to move it because I can't have both on the screen. But for number 1, we have the same picture. So it's the same idea, but our chart is going to change. So I want to show you on this one, the reason I have this on here is to show you how important it is to make sure you're labeling everything correctly. Okay, let's look up at your picture above and let's do this. You know what, let me draw this. I was being lazy, but we really need it so we can see it. Suppose now the boat is moving at 4 feet per second. So now we have a rate, but now it's dx dt. The reason I have a negative on there is because look at, this is the boat here, and if it's traveling left, this gap right here, this x is decreasing, okay? Determine the speed at which the wind. So now I want to know how fast this is going up. So I want to find dr dt when there's a total of 13 feet of rope out. So now r is 13 feet. And we still know that y is our constant. Look up above at the two charts. Okay, in this case, they gave me the speed. What was that? The speed at which the rope is pulled in. And in this one, they gave me the speed of the boat. Okay, so we have dr dt above and dx dt down here. I'm going to let you try this one on your own. It's very similar to the one above. And then you can check the completed notes for your work. Okay, going on to this one. So we have this 10-foot ladder leaning up against the school wall. The lower end of the ladder begins to slip away at a rate of 2 feet per second. When the lower end is 6 feet away, how fast is the ladder sliding down the wall? Okay, this is a classic problem here. Let's call this X, Y, and R again. Okay, looking at this one, we have our table now. Constant. At least you have a nice picture here. Changing in rates. Okay, let's go through and read and classify. A 10-foot ladder. Okay, look at the ladder here. Is the ladder always the same size? It is, so there's a constant. So R equals 10 feet. The lower end begins to slip away at a rate. They're telling us we have a rate of 2 feet per second. So if the lower end is slipping away and it's going this way, okay, so the lower end is slipping away, that's a rate, that's dx dt. That's why it's important for you guys to label these. Now, as it slips away, doesn't this x value grow? So I'm going to leave it positive. Okay, if you look back up above at the boat one, the x value was shrinking, so we made it negative. Okay, let's keep going. Where are we at? Slip away. When the lower end is 6 feet away. It's not always 6 feet away, just at this moment. So what is 6 feet? The lower end, which we'll call x. Find how fast, that's a rate. So d something dt. When the ladder is sliding down the wall, do you guys see that this ladder is sliding down the wall? So we want to find dy dt. Okay, are there any, well, what equation? Pythagorean. Are there any constants? Ooh, good call. Yes, there are. R is 10. So we have x squared plus y squared equals 100. On to the derivative. 2x dx dt plus 2y dy dt. And 0. Oh, that's lovely. The derivative of a constant is 0. Look, guys, if you forgot to sub in the constant, wouldn't you have gotten 2r dr dt? And do you see that there's no dr dt up here? That would have been a red flag that we made a mistake. Divide everything by 2, throw some numbers in. X gets replaced with 6, dx dt with 2. Y gets replaced. Oh, we don't know what y is. How are we going to find y? Oh, remember we did this thing before? That if r is 10 and x is 6, we can use Pythagorean theorem. X squared plus y squared is r squared. So y squared is 64, y is 8. Hey, if you guys remembered your Pythagorean triples, remember it goes 3, 4, 5. So if you cut these in half, you'll see that it's 3, 4, 5, and that's how we got the 8 there. 8 is 4 doubled. Okay, so now we can go over here and say, well, y is 8, and dy dt is what I want to find. So now I have 8 dy dt. I'm going to throw this 12 to the other side. So dy dt is, Okay, this will reduce to -3/2. What units go on it? Well, dy, so the y is measured in feet and time is measured in seconds. Okay, going on. So ladder problem is a pretty popular one. Wanted to make sure you got that one. Okay, look who's up. We have some angles now. Okay, this is going to be the last one. Let's go ahead and draw our picture. We still have r, x, and y, but now it says how fast is the angle between the ground and the ladder? Well, here's your ladder, right? So here's our angle. So we want to know of our constant changing in rates, all of this should be the same, right? We have all this as above, so we really don't need to copy it over if you don't want to. We know this from above. Okay, so same situation. Now we want to find how fast the angle is, so we want to find d theta dt. Okay, so theta, we can use sine, cosine, or tangent. You want to be smart about what you use. If you use y, isn't that opposite? Okay, so if we're looking at SOHCAHTOA, a little throwback to some SOHCAHTOA. SOHCAHTOA. Okay, if we look here, we don't have any information about y. So do you get it? Would it make sense to use this one? What is that one? Isn't that opposite? So would it make sense for us to use sine or tangent? So it looks like cosine is going to be the winner. Okay, so let's say our equation would be cosine of theta equals adjacent over hypotenuse, so x over r. The great news is, what are we supposed to do, guys, before we move on? Aren't we supposed to sub in constants? So we're going to have 10 over, I'm sorry, let's erase that. X is not a constant. The constant is r. If you sub your constants in, it just makes your life easier, right? You got rid of a variable. Step 4, let's take the derivative. Before we go on, though, to take the derivative, wouldn't it make sense to write this as 1/10 x in case we didn't see it like that? We don't want to use quotient rule if we don't need it. Okay, derivative of cosine is negative sine theta. And then remember chain rule, the derivative of the inside, we're applying the operator d dt, so we get d theta dt. 1/10 is a scalar, derivative of x is dx dt. Let's start on the right. It's a little easier because we know dx dt is 2 from above. D theta dt is what we're trying to find, so that's fine, and we have a negative. So what we need to find is sine of theta. Now, it would be so nice if they told us what theta is, but they didn't. But you guys, remember what sine is. It's opposite over hypotenuse. Now, I showed the work over here. Let me show you what I did. Right now, all we know is that x is 6 and r is 10. X is 6 and r is 10. But sine of theta is going to be opposite over hypotenuse. I just copied this triangle from above. Okay, so opposite over hypotenuse is going to be 8 over 10. So d theta dt, I'm not going to reduce this because I think some things are going to get canceled. We're going to get 2/10 times a negative 10/8. So this means d theta dt is going to be negative 1/4. Theta, which is the numerator, is in radians, and the bottom is measured in seconds. So we get negative 1/4 radians per second. Okay, done with our notes from not particle motion, related rates. Okay, see you guys.